Welcome back to our lecture series on automated machine learning. And now we would like to dive a bit deeper in how to formally define automated machine learning. So let's see how we're doing that. Let's start with machine learning, because automated machine learning sits more on top of machine learning itself. We need to be clear on what that actually means. So we're saying we have a data set, and as always, let's assume something very simple. Let's say we're doing that in a supervised fashion, where we have input vectors and output labels. Of course, you could also do multi-label system and whatsoever. Let's make it simple for the moment, right? And we're saying we have a hypothesis space, actually, with all possible predictive models under consideration. And what we so more is doing is saying we would like from that kind of hypothesis space finding a model, let's call it F, and we have something which is called an empirical risk, given that, so our model adds the data set. So more easy to say is more how likely is it that you are doing an error given our data sets on that model. And of course, we'd like to find the best model given the data set in our hypothesis space. How to do that in practice, what it means to make an error. So empirical performance can be very easily done for supervised learning, where we simply say, okay, we have some kind of a loss function on two labels. So we have the original one from our data set, right? So that goes in here. And then with the input xj or xi to our model, the model should also produce a label, so a prediction number, we call that. And we simply compare whether the original label and the prediction is the same or at least similar, right? Depending on whether you're doing classification, regression, and whatsoever. So, and then what we're doing is simply summing over all our data points, for example, right? And then we can call that an empirical risk of our model given the data. So how to get the model actually in the first place is simply saying, okay, we need to add maybe a bit more to it. So we had before already data set in the hypothesis space, but what we more or less not talked about so far is that we can make certain decisions on the model. For example, what kind of model are we talking about, or what kind of hyperparameters? So we have a configuration space, and what we now actually doing is having what we call an inducer, or the learning algorithm. You can both say, but most of the time I will now use inducer as the wording. And the inducer is the algorithm which maps now the data set, and given a hyperparameter configuration, to the hypothesis space, or if you have concrete elements to it. So one very concrete data set with a very concrete fixed hyperparameter setting is mapped to one model. And of course, we still would like to minimize by doing that the empirical risk. Why is it now important to talk about this kind of configuration and inducer? So inducer, let's simply assume that our inducer is something like stochastic gradient descent, SGD, because what we're feeding in is more the data. The hyperparameter, the configuration could be defining for our architecture and the learning rate. And now SGD as the inducer has the task of doing updates over and over again in a way that with the given learning rate, for example, with the given architecture, that eventually we're ending up to a model which hopefully then minimize the empirical risk. What can be described with our configuration space? Actually quite a lot. So we can talk about hyperparameters. For example, our lambda could specify the setting of learning rate and data accumulation strength, but it could also define the architecture itself. So for example, what kind of operators or connections of its cell in a neural network is often done. We can also talk about entire pipelines. So we can also talk about whether maybe first applying a PCA and then feeding that kind of transformed data into a linear model, or whatsoever. So you can also encode more entire pipelines via this kind of lambda configuration space. Or ensembling. We can also say, okay, we don't want to find a single model, but maybe a set of models, which we combining then, for example, with averaging or stacking or whatsoever. And the question is, okay, what kind actually of of models we'd like to have in our ensembles, or maybe even how to combine it. All of that are design decisions which are or could be included and encoded in Lambda and the configuration space. So now putting that a bit more on the next high level, because in practice, we don't really have these kind of empirical risks directly, but we have to distinguish between the training data set to train our model and the validation data set, which we now are using to decide what is the best configuration actually. So now we're saying not that the configuration from our configuration space is given, but actually we're saying that we'd like to find the best configuration, which is then feed into the inducer, and that gives us, of course, the model. But let's say it from that kind of perspective that we're finding now the best configuration. So it's again an argmin. Now we're saying we have generalization risk, which on the one hand, the inducer gets the training data set and the configuration, produces now our model, and it gets also in addition validation data, which is of course disjoint from the training data that we get an unbiased estimator of how good the found model actually performs. And since we're doing here more as now these kind of argmin, typically means we evaluating different kind of configuration over and over again, we need to really this kind of validation set, which is then evaluated several times. As a side note, in practice, what we also have is the test that we can evaluate our final configuration on another disjoint set, which allows us then to figure out in an unbiased way how well even that performs. As a summary, the learning of the machine learning model focuses on minimizing the training error, which should eventually lead to better generalization error overall. That's the hope we always have. To that end, we're using inducer, which we also call a learning algorithm, and the configuration in addition, and putting both together on a given data set, and we get one model out of that. Automated machine learning is now more or less sitting on top of that kind of deciding the configuration. Because the optimal configuration should lead to better performance of the inducer, giving us a better model, so which means minimizing generalization error. There are different ways on how to do that kind of evaluation scheme, how to think about also random numbers and all of that, and that will be discussed in other sessions. I won't go into detail here. Only saying what I showed you more than saying there's training, there's validation, there's tests is the most simplest way to think about that. It's actually in practice often a bit more complicated. But for understanding what we're doing, what AutoML is actually meant to solve, I think that's now quite nice to have a first formal understanding on what we can do. Good. With that, I think you have a good understanding, and I hope I see you again in the next video.